Swayam Prabha. Digital India. Educated India.
Welcome to lecture number 19, part 2. Continue with the topic food deterioration model and shelf life testing. So, in the previous lecture, that is lecture number 19, part 1, we have seen three types of kinetic model. One is zero order kinetic model, first order, and Arrhenius model. While I was explaining the different types of models, forgot to tell the examples, especially for the zero order and for first order. If you take the zero order kinetic model, so it can be used for modeling, to model the, to predict the shelf life and the quality changes in case, especially in kiwi fruit, and also the dried coconut chips, that the quality change, how does the color changes, that also can be analyzed by using a zero order kinetic model. When it comes to first order kinetic model, the degradation of the apple, that is due to the presence of ascorbic acid, that can be modeled during using the first order kinetic model. In the previous lecture, that is lecture number 19, part 1, I have solved one numerical question that was based on Arrhenius model. So, we will continue with a couple of numerical questions. Then I will be discussing about the other models, either in this lecture or in the subsequent lecture, depending upon the availability of the time. So, let us go to the numerical question number 2. At a temperature of 600 Kelvin, the rate constant of a chemical reaction is 2.75 into 10 power minus 8 per mole second. So, the rate constant is represented by the letter K. N is the order of the reaction, K is the rate constant. When the temperature is increased from 600 to 800 Kelvin, again the rate constant is, value is given. It is 1.95 into 10 power minus 7. 1.95 into 10 power minus 7 per mole per second. What is the activation energy of this reaction? Okay, so, let us solve this numerical question. So, this is the second numerical question based on Arrhenius model. Let us write the given data. Temperature, two temperatures and two rate constants are given. So, let us use T1. T1 is 600 Kelvin. This is T1, this is K1. This will be T2 and K2. 600 Kelvin, 2.600 Kelvin. And T2 is 800 Kelvin. Corresponding to T1, the rate constant value is K1 is 2.75 into 10 power minus 8. 2.75 into 10 power minus 8 per mole per second, and corresponding to T2, the value of K2 is 1.95 into 10 power minus 7. 1.95 into 10 power minus 7 per mole per second. So, that is the SI unit. So, we have to find out the activation energy. What is the activation energy? Activation energy of this reaction. So, that is capital E. So, to find what is capital. So, this is also based on Arrhenius model. So, this problem is based on Arrhenius model. So, let us solve this one. So, Arrhenius model is K equal to A into E power minus capital E by RT, where R is the gas constant, that is 8.314 joule per mole Kelvin. T is the temperature in Kelvin. So, here since two temperatures and two rate constants are given, I will be using the subscript 1 and 2. According to Arrhenius model, K is equal to A into E power minus capital E by RT. Since there are two rate constant and two temperatures, so for the first condition, I will write K1 T1. K1 into T1. Okay, so that's what I have written here. So K1 into A into E power minus capital E. Capital E is the activation energy. R into divided by R into T1. Let this be equation number 1. Take ln on both sides. Therefore, equation 1 becomes equation 1 becomes ln of K1, that is on the left hand side, ln of A into E power minus E by R into T1. That's what I mentioned here. Okay, so ln of K1 into ln of. So the right hand side, there is only one term on the left hand side. On the right hand side, there is a product A into exponential term. So I will be splitting. So ln of K1, this is equal to, there is a product term here. So we will be splitting ln of A plus ln into E power minus capital E by RT1. That's what I have mentioned. Ln of K1 equal to ln A plus ln of E power. This will be equation number 2. If you want, you can put a bracket here. Equation number 2. Similarly, we can write equation for the second condition when the temperature is increased from 600 to 800, K1 from 2.75 into 10 power minus 8 per mole per second to 1.95 into 10 power minus 7 per mole per second. Similarly, ln of K2 is equal to ln of A plus ln of E power minus capital E by R into T2. Instead of T1, you would write T2. E by R into T2. So this will be equation number 3. Subtract equation 3 from 2. So of course here I am using a different equation. So let us follow the equation number which I have used in PPT so that it will be easy for the learners to refer. So this will be equation 1. So I have not given equation number for this equation. So let us have this one. So this will be equation number 1 and this will be equation number 2. Subtract equation 2 from 1. Equation, let me write it. So write equation 2 minus, sorry, 1 minus, subtract 2 from 1. So it will be equation 1 minus equation 2. Left side it will be in equation number 1 it is ln of k1. Left hand side of equation 2 is ln of k2, so minus ln of k2. Coming to the right hand side, ln a and ln a will get cancelled. So ln a minus ln a. Right hand side, there are two terms, ln a and ln a. It will get cancelled. Plus the second term in the right side, ln of e power minus e by rt1 minus ln of e power capital E by r into t2. So these two will get cancelled. So we will get ln of k1 minus ln of k2 is equal to ln of k1 minus ln of k2 is equal to, right side, first term will be ln of e power minus capital E by r into t1. Capital E is the activation energy minus ln of capital E minus E by r into t2. The left hand side is ln A minus ln B is ln of A by B. So it will be ln of K1 by K2. So this term ln of E will get cancelled. So you will have minus E by R into T1 minus of here minus E by R into T2. So this will become, the right hand side will become, the first term will be negative, minus E by R into T1, minus of minus will become plus, plus E by R into T2, ln of K1 by K2. After deriving the equation, I will be substituting the values to complete this numerical question. So ln of K1 by K2 equal to minus E by R into T1 plus E by R into T2. So let us take E by R as a common term, right side. If you take E by R as a common term, the first term it is minus 1 by T1 and in the second term 1 by T2. So this can be written as E by R into 1 by T2 minus 1 by T1. Left hand side will be ln of K1 by K2. So if you see the given data, K1 is given, K2 is given, T2 is given, T1 is given, and R we know the value 8.314 joule per mole Kelvin. So substitute all the values, okay, substitute all the values, we will get the value of E. Substitute the values of K1, K2, T1, T2 and R. R is equal to 8.314 joule per mole Kelvin. That is a standard value. And solving we get capital E is equal to the activation energy which is expressed by the letter capital E, that is equal to 39,040 joule per mole. 39,040 joule per mole. So that completes this numerical question. Let us solve one more numerical question based on Arrhenius model before moving to the next topic. Orange juice is typically packed in a multi-layer carton boxes. So at the moment of packing, the juice contain minimum 50 milligram of vitamin C per 100 gram. Contains 50 mg of vitamin C per 100 gram. The label claims a vitamin C content of 40 milligram per 100 gram. What must be the maximum or maximal storage temperature if the product has to comply with the claim on the label after 180 days of storage? Assume that the loss of vitamin C follows a first order kinetics with a rate constant of 0.00441 per day. Rate constant is K and the energy of activation is 7000 joule per mole at 27 degree centigrade. So let us solve this one. So the C naught value is given, C value is given. So this is numerical question number 3. C naught is 50 milligram. C is equal to 40 milligram. Ca. This is C naught and this is Ca. So this is C naught. This is C naught and this is Ca. Activation energy is given 70,000 joule per mole. Initial temperature is given, T1 is 27 degrees centigrade. Rate constant is given 0.00441 per day. K1 is equal to 0.00441 per day. Initial temperature is given as 27 degrees centigrade converted into Kelvin. And the time period is given as 180 days. T is given, small t is given, which is about 6 months. Okay, so this is since time period is given and it is clearly given that first order kinetics. Assume that the loss of vitamin C follows a first order kinetics. First order kinetics. So first we will be using the first order kinetic model equation, that is ln of Ca by Ca naught is equal to Kt. Okay, so this will be Ca naught. This is Ca, this is Ca naught. According to first order kinetic model, so ln of Ca by Ca naught is equal to Kt. Ln of Ca by Ca naught is equal to Kt. Let the rate constant at unknown storage temperature be K2. So I will modify this equation. Let the rate constant be K2 at unknown storage temperature. Let the rate constant be K2 at unknown storage temperature. So the above equation will be written as ln of Ca by Ca naught is equal to K2 into T. This is what I have written here. So Ca value is given, Ca naught value is given, time is given 180 days. So solving, we will get the value of K2. Substitute the values of Ca, Ca naught and small t, we get ln of 40 divided by 50 equal to K2 into 180. So you'll get the K2 value as 0.00124. This is the rate constant value at the unknown storage temperature. K2 is equal to 0.00124. So now I will be using the Arrhenius model equation. That is the equation which the simplified form of the equation which was used to solve the numerical question. Ln of K1 by K2 equal to E by R 1 by T2 minus 1 by T1. So this equation was derived when we are solving the numerical question number 2. According to Arrhenius kinetic model, ln of K1 by K2 is equal to I think E by R term is common term. Yes. E by R is a common term. In bracket 1 by T2 minus 1 by T1, where T2 is the unknown temperature which we have to find out. You see the question, what must be the maximal storage temperature? So this is the question, what must be the maximum storage temperature, which is unknown, which we have to find out. So here we can write to find, let me write it here, to find T2, that is unknown temperature. So K1 is given, K2 we have found, E value is given, R value 8.314 joule per mole Kelvin, T1 is given. Substituting all, the only unknown is T2. Solving, we get T2 is equal to 287 Kelvin. 287 Kelvin, which is equal to 14 degree centigrade. So that completes the numerical question. So far we have solved 3 numerical questions, one in part 1 and the other 2 are in part 2 of the lecture number 19. Let us move to the next model, that is the Q10 model. This is the second type of kinetic model. It estimates the changes in the reaction rate for every 10 degree centigrade change in temperature, that is increase in temperature. Because it monitors the how does the reaction rate changes for every 10 degree rise in temperature. So this model has got the number 10 in the name itself. That is why it is called Q10 model. That is why it is called Q10. This 10 refers to for every incremental temperature of 10 degrees centigrade, how does the rate of reaction changes. This is also used to predict the shelf life of the food product under varying temperatures. For every increase in 10 degrees centigrade, the reaction rate is assumed to be doubled. For most of the products. However, the actual reaction rate can be estimated based on the data given in the problem. We can estimate it, but otherwise it is assumed that for every 10 degree rise, the reaction rate is doubled. It is not an accurate method for products with complex degradation mechanism. It is not accurate method for products with complex degradation mechanism. This model is recommended to perform stability test at different temperatures. So as I mentioned before, this model is used to predict the shelf life for varying temperatures. So it is recommended to perform the stability test under different and varying temperatures. To validate this method to ensure accurate shelf life prediction. So I will stop at this point. So I will be continuing this topic in the subsequent lecture. Thank you.